All right, let's prove this recurrence equation together. The base case is when k equals 0, if we're just putting k equals 0 here and here, then that is t1, which is 0. Because we claim that stated that when n equals 1, then the output is 0. All right. So for the base case, this claim is true. And we're going to think about the inductive step. If k is larger than 0, we assume that t to the power of k minus 1 equals this one. So we're just assuming that when k n is k minus 1, this one holds. Then t to the power of k, you are going to use this part. It's going to be 2 to the power of k minus 1 times 2, plus here we are substituting n as 2 to the power of k. So we are putting 2 to the power of k here. And we know that this one is k minus 1 times 2 to the power of k minus 1. So we are putting this value here. And here we have 2. And by combining these 2 to the power of k minus 1 and 2, it's going to be k times 2 to the power of k. So we just proved that using mathematical induction, that t 2 to the power of k becomes k times 2 to the power of k. And we are just returning back to n, because 2 to the power of k is n. K becomes log n, right? And we are putting this value here, then tn, because n times log n. And this one is smaller than n squared, right? So that is why recursive implementation is faster than the faster version. All right. So any questions about this proof? All right, thank you for your feedback. As we saw in our experiment, when n becomes larger and larger, the speed gap becomes larger as well. And so this one was naive solution. This one was faster version. This one was recursive version. And for n equals 10 to the power of 6, the naive solution requires 3 times 10 to the power of 17 computations, while the faster version requires 5 times 10 to the power of 11. Whereas the recursive solution takes 2 to the power of 10, 2 times 10 to the power of 7. For 1 gigahertz processor, this means it could perform 10 to the power of 9 additions per second. So when n becomes 10 to the power of 6, the naive solution requires 3 times 10 to the power of 8 seconds. This one is same as 10 years. And the fast solution requires 5 times 10 to the power of 2 seconds, which is same as 8 minutes. And the recursive solution takes only 20 milliseconds. using the same 1 gigahertz processor. So this one demonstrates that efficient algorithms really saves the computation. All right. So now you might all of you might understood the importance of efficient algorithms. However, I told you that when n was small, recursive solution was slower than a faster version. I told you that recursion entails function calls, and function calls sometimes requires more overhead. And you better weigh between the overhead and performance gain. So when n is small, you might use the faster version. And when n becomes larger, then you might turn to recursive solution. And my last question is, our recursive solution was quite amazing. However, the fact is, we can do even better than our recursive solution. And you can think about how we can even improve our recursive version. And this might be one of our homework problems. And another takeaway from our class is when you see these implementations, the faster version is shorter than the recursive solution. The recursive solution is quite longer than this faster version. So shorter implementation or constant implementation don't necessarily mean that they are more efficient. Okay? So even though your code or your implementation can be longer, but it could be more efficient. Okay? And from now on, we're going to talk about theoretical analysis. Counting the number of primitive operations that an algorithm executes in the worst case on an input of size n is what we are going to do. Since all primitive operations take constant time on modern computers, so we are just count the number of primitive operations like addition, subtraction, or multiplication, division, like this. If the fastest primitive operation takes time A and the slowest time B, and the algorithm of interest uses P and primitive operations, then the total number of operation is bounded by B times Pn and A times Pn. So our computation is bounded by these two numbers. And examples of primitive operations are assigning a value to a variable or calling a method, arithmetic operations, adding to numbers, or indexing into an array, or following a reference, returning from a method, these kind of things. We are actually more interested in the growth rate of the running time rather than the exact number of additions or exact number of primitive operations. The growth rate indicates how fast the running time increases when the size of input increases. So why is this important? Because the growth rate determines the scaling behavior, as we saw in the previous example. So when n was small, the three solutions came up with a solution with a similar amount of time. So when n is small, you don't need to care about whether it is efficient or not. However, when n becomes larger and larger, the time gap become larger as well. So the time complexity, let's say the time complexity is n or n squared n cubed 2 to the power of n. Problem size after speed up becomes 10 times like this. And there is one big, so we are going to here introduce some notations to describe the complexity growth rate of our algorithms. The first one is big O notation. So big O notation represents the growth rate of an algorithm, and the goal is to specify the bounding from above. So let's have a look at this graph. So let's say this fx, this function, is bounded by 2 times gx. So this one is smaller than 2 times gx all the times. Then we could say when x is here, this one is x-axis, this one is y-axis. When x is larger than 1, then this function is always smaller than 2 times gx. Then we say f is in G's bounded above family, or f is inside big O of gx. Even though fx is larger than gx, but smaller than 2 times gx, we don't care. If we can multiply some constant, and this gx could be larger than this fx, when x is larger than 1, then we just say fx is inside G's bounded above family. So more precisely, we say that fx is inside the big O family of gx if there is a real number c larger than 0 and an integer n0 that is larger than 1, such that fn is always smaller than c times gn for n larger than n0. So if, let's say, this value is like 3, even in this case, or 3 or 2, even in this case, we say that f is inside the big O family of gx. All right? And there is another notation that is called big omega notation. This is similar to big O notation. We're going to specify the bounding from below. So we're going to focus on the lower bound. Here, f prime x, this f prime x is larger than 0.5 times gx, as long as x is larger than 1. Then we say f prime x is in G's bounded below family, even though f prime x is smaller than gx everywhere. All right? So more precisely, if we can find the real constant number c larger than 0 and an integer n0, such that fn is always larger than c times gn when n is larger than n0, then we say f is inside the big omega of g. Okay, you just need to find g and n0, c and n0. And as you saw these two examples, then you could say that, oh, the same g can be a big family of so you can think about this case. So the same G can be a big O of F as well as the big omega of F. This is possible, okay? So you just need to be able to find this constant C and this N0 integer. And the last notation we're going to think about is big theta notation. In the two previous slides, we not only have F was a family of big OG, and F prime X was family of omega G. But also, this one happened. This is what I told you in the previous slide. In this case, we say that Fx is the family of big theta of G. So if G is big omega of F, as well as big omega of G, then we say F is in the family of big theta of G, okay? So if we say F is in the family of big theta of G, that means G can be the family of big O and the family of big omega for F. So this is our notation. And we represent the complexity with the simplest form. So let's say the time complexity of this one, we do not care about these small numbers and even the constant. As you saw in the previous slides, or the definitions of big omega, big O, big theta notations, we don't need to care about these constants. We only care about this number. So the simplest term becomes big O n squared. And in this case, we remove the smaller time complexity terms and the constant, and we just say time complexity of this algorithm is big O n cubed. In this case, we do not care about these numbers, and the time complexity becomes big O of log n. In this case, we remove this part and remove this part. So when we basically analyze some algorithms, we usually use the big O notation. So that is the best basic case. The reason is, let's say when n becomes these values, and these are some time complexities. As you can see here, when n becomes very large, like this, when you compare 2 to the power of n and 2 to n cubed, you don't have to care about this number because the dimension is different, very, very different. Even though you multiply like 1,000 or 10,000, any numbers, it is much, much larger than n cubed. So we do not care about n cubed when there is 2 to the power of n. And when you look at these two terms, n log n becomes meaningless compared to n squared when n is large, like this. So we do not care about this term, but only this term, okay? So this is why I only care about the biggest terms and remove the smaller terms. And this is going to be, I guess, the last PPP exercise of today. Sort the functions in the increasing order of big O complexity.